1,000 feet down, the ocean presses with enough force to crumple a steel drum like paper. Submarines sail there anyway. At crush depth, a hull failure takes milliseconds. Sailors would be gone before their brains could register the sound. Yet for over a century, humans have built machines to live inside that pressure, on purpose, for months at a time. The ocean does not forgive miscalculation. Every foot of depth adds nearly half a pound of pressure per square inch. By 600 meters, that pressure exceeds 60 times what the human body feels at sea level. Early inventors understood the danger long before they understood the engineering needed to survive it. In 1620, Dutch engineer Cornelis Drebbel rode a leather-covered submersible beneath the Thames, more curiosity than warship. 2 centuries later, the American Civil War produced the Hunley, a hand-cranked iron tube that sank the ships it attacked. These vessels barely dipped below the surface. True depth remained a mystery no one had dared to test. But here is where it gets stranger. The real breakthrough came not from weapons, but from geometry. Engineers discovered that a cylinder resists crushing far better than a box, distributing pressure evenly across its curved skin. This single insight, the pressure hull as a perfect circle in cross-section, became the foundation of every modern submarine. Picture the hull as an eggshell. Round shapes spread force evenly, while flat panels concentrate stress until they buckle. World War II submarines dove to around 90 meters, their riveted steel hulls groaning audibly under the strain. Crews learned to read those groans like a language, listening for the difference between normal stress and impending failure. A single weak rivet, a hidden flaw in the steel, could turn a routine patrol into a silent catastrophe. So naval architects began asking a harder question: how deep could a submarine go before physics simply refused further argument? The answer depended entirely on materials science, a field that would transform submarines twice over the next 50 years. Nuclear power changed everything in the 1950s, freeing submarines from surfacing for air and letting them dive deeper, longer. But nuclear power alone could not solve the crushing math of depth. That required a revolution in steel itself. What nobody expected was how much a small change in alloy chemistry could extend a submarine's survivable depth by hundreds of feet. HY-80 steel, developed for American submarines, could bend under stress instead of snapping, buying crucial margin against failure. Later, HY-100 pushed that margin further, allowing hulls thick enough to survive deeper water without becoming impossibly heavy. Thickness alone was never the answer. A submarine built like a bank vault would sink and never rise again. Engineers had to balance strength against weight with a precision closer to aircraft design than shipbuilding. Every weld became a potential weak point, so shipyards developed exhaustive inspection routines, testing seams with sound waves and radiation. A flawed weld invisible to the naked eye could still doom a vessel decades later, deep beneath the waves. This obsession with inspection was not paranoia. History had already shown what happens when it is ignored. In April 1963, the USS Thresher, the most advanced submarine of its era, dove for a routine test off the Atlantic coast. It never surfaced. All 129 aboard were lost when the hull is believed to have failed under pressure. Investigators later pointed to a possible piping joint failure that triggered flooding, followed by catastrophic pressure collapse. The disaster reshaped submarine safety forever, leading to the SUBSAFE program, one of the strictest engineering standards ever created. Every valve, weld, and seal below a certain depth threshold now required documented, traceable certification before a submarine could dive. But here is where it gets stranger. Since SUBSAFE began, no certified American submarine has been lost to a similar disaster. That track record is not luck. It is the direct result of treating every bolt as a potential point of failure. Meanwhile, Soviet engineers pursued a radically different path, betting on a metal far stronger and far harder to work. Titanium alloy hulls, lighter and stronger than steel, allowed Soviet submarines like the Alpha class to dive deeper and faster. Titanium resisted magnetic detection too, but welding it required specialized chambers filled with inert gas to prevent contamination. The cost was staggering, reportedly consuming a significant share of Soviet shipbuilding budgets for a single class of vessel. Depth had become a currency nations were willing to spend fortunes to buy, foot by punishing foot. Picture a submarine's pressure hull as a chart of concentric rings, each layer of steel calculated to bend, not break. Modern attack submarines are believed to operate safely to depths of around 250 to 300 meters, though real limits stay classified. Crush depth, the point of no return, is estimated at nearly double that for many modern designs. Navies guard these numbers closely, since knowing an adversary's true limits offers a dangerous strategic advantage. What nobody expected was how much psychology would matter as much as steel once crews approached these limits. Submariners train for the sound of hull compression, a series of sharp cracks and pops as depth increases. Those sounds are normal, the hull flexing exactly as engineers intended, but they test the nerves of every new sailor. Veteran crews describe it calmly. Rookies often describe it as the loudest silence they have ever heard. Beyond the hull itself, submarines rely on internal systems just as critical to surviving depth as the steel around them. Ballast tanks control buoyancy, flooding with seawater to dive and blasting it out with compressed air to rise. A failure in these systems at depth leaves a crew with almost no room for error and very little time. Life support systems scrub carbon dioxide and generate oxygen electrically, letting nuclear submarines remain submerged for months without surfacing. But here is where it gets stranger. The deepest a crewed vehicle has ever gone is far beyond any submarine's design. In 1960, the Bathyscaphe Trieste reached the Challenger Deep, nearly 11,000 meters down in the Mariana Trench. Its crew cabin was a thick steel sphere, the strongest shape known for resisting pressure from every direction at once. At that depth, pressure exceeds 16,000 pounds per square inch, more than 1,000 times surface conditions. No military submarine attempts anything close to that depth. Spheres survive there, long cylinders were never built to. The shape that saves a deep-sea explorer would be useless for a warship needing speed, weapons, and living space. Every submarine design is ultimately a negotiation between three enemies: pressure, weight, and the mission it must perform. Modern shipbuilders now use computer modeling to simulate millions of stress scenarios before a single hull plate is cut. Sensors embedded in test hulls measure flex in real time, feeding data back into designs for the next generation. Some navies are experimenting with composite materials, hoping to push depth limits without repeating history's costliest mistakes. Yet even with all this precision, submarines remain, at their core, a bet against an ocean that never stops pressing. Every dive is a controlled negotiation with forces that would otherwise instantly reduce a hull to twisted scrap. The margin between routine patrol and disaster is measured in millimeters of steel and years of disciplined inspection. That margin is why the loss of the Thresher still shapes engineering decisions made in shipyards more than 60 years later. Every certified weld, every pressure test, every silent creak in the dark is a direct answer to that lesson. Submarines do not defeat the ocean's pressure. They negotiate with it, foot by foot, dive after dive. Somewhere right now, a hull is groaning under the deep, and a crew is trusting the math that keeps it whole.